As you've probably, I don't know if discovered is quite the right word, but I keep telling you I'll have an assignment to you by the end of the day. And I think I've told that to you 2 or 3 times at this point. It will actually happen today, but through discussions with Akiva, we've changed my original idea into a two-parter. And so this basically in any class that I teach, I want at least one of the outcomes of this to be a large-scale project that you can put in your code portfolio. Something that you could show in an interview that says, this is what I've done, this is what I'm capable of. And if you don't do that in your classes, then you have to come up with projects on your own to demonstrate what you're capable of. So I try to build that into the classes wherever I can.
Okay.
And I had originally thought this would be something like a 2-week assignment, but breaking that down into 2 1-week components of that assignment, I think makes a lot more sense. So the first week of this will be focused on the actual graph structure, and the second week will be implementing the algorithms into that structure. But we've complicated it a bit and thrown in an inheritance hierarchy. And so we're going to be kind of whatever it is that you learned in 211, we're going to be putting that into assignments that we give you from here on out. So that would be a good way to demonstrate everything that you've learned in prior classes and incorporate it into the material that we've learned in this class. And my goal with that is that you have something to show off from this class that will be long-term beneficial to you. So that's why it's taken a bit to design, but I'm really happy with the design that we have. We're in the process of writing it up. So we should have that to you by the end of the day. At this point, you probably shouldn't believe me when I tell you these things, but I'm more confident than ever that we'll have it to you by the end of the day, especially if the first part of this is going to be due next Wednesday. And that will just be the structural components of graph.
But if it was preferable to have just one thing.
We thought about it. And if we did that, then I think what would happen is we would overwhelm those of you who would procrastinate this until the last week.
That would be something. Specifically if beyond 8, I'd definitely do that. 2-week project, that sounds like 3 days.
I wonder what my brother would say if he was here, because I know he has a tendency of procrastinating like that.
So that's an update on that. So you can expect that by the end of the day. Part 1 for this should be due on Wednesday. Although given that it is a 2-parter, I'm probably more willing than usual to give you an extra day. If you're studying for the exam, focusing on the exam, get started over the weekend, can't get very far because you get stuck, come to me on Monday, and you need an extra day to just iterate and make sure that works. I'll probably be more open to that than usual. I'm usually open to it, but I'm a little bit flexible on a 2-parter.
But if in my hubris, I think I can do this 2-week project in 1.
All right, I'm making it harder. No, I'm kidding, I don't do that. All right, so today is our first review day. We'll see at the end of the class if we want to cycle back to any other components for review. As I mentioned yesterday, I have 4 problems prepared for the moment, but I want to start today's class by asking if there are any questions on the study guide or clarification, what you should be doing or focusing on before we dive into some practice problems. I can also circle back to this at the end, yeah.
Sorry, forgot.
Yeah.
You were just asking out of the study guide what we like to focus on.
Yeah.
Honestly, identify like if like where the read algorithms are applicable.
Yep, that is what I have prepared for today because I knew that was going to be the challenge.
Oh yeah, hey, one more thing about you mentioned in your hubris. Yeah, to be careful if you know you have your own hubris, because that is because hubris makes you feel really powerful, but then the next thing you know, you'll get slapped in the face by it after getting defeated in the worst way possible.
Say that now. On my Wednesday.
Other questions from the study guide?
I speak from experience.
All right, I'll try to stop this a little bit early. If you're working on this and find yourself with a little bit of extra time, or you can take a look at the study guide, see if you have some questions, and I'll try to circle back to it at the end of class. But let's take a look at the first problem. I can zoom in on this so it's a little bit easier to read. So I pulled 4 problems. This is the first one. So this is going to be very similar to the style of what I plan to throw in the exam. The questions that you should be asking in order for something like this is come up with a dynamic programming solution. Once you have a dynamic programming solution, ask yourself, what is a greedy assumption that we could make? Once you have a greedy assumption, ask the question, does that greedy assumption lead to an optimal subproblem breakdown? Does making that greedy problem give us an optimal answer? And does that, once we have that optimal, once we think it's an optimal answer, either what is the breakdown of that, go logically show it, or find a counterexample that says that here is a problem instance where making the greedy assumption does not give us the optimal answer. So a broken calculator is a calculator that can only do 2 things. It can double the number or it can subtract 1 from the number. And so we take a starting value and there is a target. We want to find the minimum number of operations where all we can do is double the number or subtract 1 from the number in order to get to the target.
Nice.
Again, part 1 of this is think about the breakdown. What are the overlapping subproblems? And see if you can come up with a dynamic programming solution to this. And then analyze maybe the runtime order of that dynamic programming solution based on something about the start value and the target. So I'll give you the hint now that some of these problems will have an optimal greedy breakdown and some of these problems will not have an optimal greedy breakdown. And I'm not telling you that in advance because I want to simulate a bit of an exam setting where you're not going to know, I'm not going to tell you in the problem, it will be up to you to determine whether a greedy breakdown is optimal or not.
Great. Ah.
Any other thoughts so far? Yeah,
My thought so far is, first of all, start by checking if start value is or multiple of target value.
Okay.
Such, and then check whether or not doublet, and then if it is, double start value. Then if it isn't, you check whether or not doubling start value would put start value at greater than target or less than target. If it puts it as greater than target, you -1 start value, then check again.
interesting.
And then I think just repeat that.
Does that lead to an optimal answer all of the time?
No, maybe.
I think it's a really good approximation.
I honestly think he was definitely on the right track.
I agree.
So I was trying to think about that too, and I actually literally just, for the first example, I literally just drew this little tree here.
Yeah,
So, like just going down, which it has to pick between two operations, like two if statements repeatedly until you find the target.
yeah. So if we're brute forcing this just
Right.
becomes a recurrence relation where we have two different things that we can do. So as we break down into two subproblems. The
Yeah,
subproblem of the number if we subtracted one, the number if we doubled.
I feel like there's something I was missing during that whole thing, that I haven't exactly mastered yet, but I definitely think not entirely on the side of the train, but please continue.
Yeah, so brute force, we could think of this as a tree where the root is the start value. Each child is a subtract one for the left child or a double for the right child, doesn't matter which left child or right child it is. And then you'd basically be doing a breadth first search in that tree until the lowest, the nearest to the root when you reveal the target. But the complexity of that is going to be exponential because
Yeah.
we're getting a tree, and depending on the depth of the solution, we'll have considered an exponential number of subproblems getting to that depth.
Yeah, I'm trying to figure out, I'm trying to remember anyway, how I should do it using dynamic programming. Try not to use any sort of notes.
Does the breakdown for that make sense with regards to what a brute force solution would look like and why a brute force solution is bad here?
Makes sense to me.
So what are the repeated subproblems? Yeah.
Yeah, trying to find the values of the result of it.
If we've ever revealed a node in this tree that is a number that we've seen before, we should prune the tree at that point and not consider because we've already been there and we've started to reveal from there. So that's an existing problem that we actually don't need to solve at all. We're in the process of solving it already. Does that meaningfully change the asymptotic runtime of the solution? What is the worst case for the number of nodes in this tree that we would eventually, if we just said, if we're going to reveal the number that has existed in the tree somewhere before? What are the most nodes in a tree that we could possibly reveal? I think we could come up with an additional trimming rule that if we have a number that is more than double the target, prune. If we're more than double the target, we're going to be decrementing so many times to get down to the target that there's no way that that's the optimal solution. So that would leave us with worst case, 2 times the value of target, number of nodes in the tree.
Research.
That is very interesting. So at least that's my setup for this problem. That's how I like to think about what are the subproblems, how can we avoid doing those subproblems, what is a worst case runtime for what problems don't make sense to try to solve. And it gives us an upper bound to the complexity of the problem. The total number of nodes in this tree is going to be less than or equal to 2 times target. But target could be very, very large.
So,
Is there a way that we could make some kind of greedy assumption from this dynamic programming approach in a way that would trim this even further? Could we analyze something about start value and target and figure out whether it makes sense to decrement or to double? What is the difference between the very first decision you make being a decrement or being a double?
less than.
I would think that there's probably going to be more. So let's say the target is a perfect power of 2, and start value is less than half of target, but it's 1 more than a power of 2. So if target is 16 and start value is 3, then you would want to decrement to 2 and then double the 4, double the 8, double the 16. And that 1 decrement was the equivalent of 4 decrements if you waited until you were above because you end up doubling so many times. The more you double, the more you have to decrement to make up for that. If you decrement earlier, then once you double, it's the equivalent of more decrements based on the number of doubles that you have. Does that concept make sense to people? When you decrement from 3 to 2, rather than doubling to 6, doubling to 12, doubling to 18, and then decrementing to 17, decrementing to 16. Yeah.
So what I'm hearing is the idea should be that we take the log of target. And I'm thinking of this right, where we just take target, if target's divisible by 2, we add it. If that's divisible by 2, we add it. And then once we get to the smallest value that can be divided by target, for instance, then after that we would then begin doubling the start value.
Yeah, so you can even start with target. That's an intriguing idea of if we started with target and tried to derive start value by either adding 1 or having the exact same problem. Thoughts on this? What do we think a greedy solution would look like? When would we want to decrement? When would we want to double?
Or double their number students.
Yeah, so if target mod start value is 0, not necessarily guaranteed, it's if the log goes in an even number of times, then you can just double into the solution. So I'll give you the hint. I think this is a good practice problem in the meantime to figure this out. There is a greedy solution to this. And I think this is something that is worth just working through because we have a limited number of these kinds of problems. Rather than just revealing the solution immediately now and talking through it, I want to give you a chance to work on that.
Okay, thanks. I was actually thinking there was definitely a greedy solution for this, but I just was not sure where to find it.
Yeah.
Or I was just trying to discern what the greedy assumption should be.
So I'm going to leave this for the moment, and we can either come back to this tomorrow. But my challenge to people over the next 24 hours is to take a look at this problem and see if you can find that greedy assumption that leads to this being optimal. Because I want to start on thinking about the next problem.
Will you put this on Canvas?
Yeah. If it's not up on Canvas by
Actually, can you zoom out a little bit, please? Like, page for some case. I am definitely planning on practicing this anyway. Way over here for study time.
So this was problem number 1. Here's problem number 2. An integer array is called arithmetic if it consists of at least 3 elements and the difference between any 2 consecutive elements is the same. So we have some subarrays here that are arithmetic sequences. We have 1, 3, 5, 7, 9. The difference between each of those is 2. 7, 7, 7, 7. The difference between each of those is 0. 3, -1, -5, -9. Difference between each of those is -4. So we're going to take a very long array and we want to find the number of arithmetic subarrays of that array. So we need at least 3 elements that have the same difference between sequential numbers. So the first example down here gives us the array 1, 2, 3, 4. The slices are 1, 2, 3, 2, 3, 4, and 1, 2, 3, 4. So again, the same sequence of steps as the last problem. Come up with a dynamic programming solution. Determine what those overlapping subproblems are. Then from there, what would a greedy assumption be or look like? Does that greedy assumption always lead to an optimal solution? If yes, why? If no, what would a counterexample problem look like?
Will the array we're passed always be an arithmetic array or
Not necessarily.
can you check?
Yeah. Yeah, example 2 shows us an example where the output would be 0. There are no arithmetic sequences in it, so it could be not long enough, or it could be long but have 0 arithmetic sequences in it.
Yeah. And I see the logic, I'm just trying to put it in code. Or just pseudocode.
Yes, the sequences do need to be contiguous in the array. You need at least 3 elements that are sequential in the array that have the same difference between each successive number.
Yeah, so. Okay. So that. Well, I've been thinking about it quite a lot so far.
It's a very interesting conclusion. What makes you think that?
Well, like if we had like 1, 2, 3, 4, like we just saw 1, 2, 3, and then you know, like okay, we can save that now.
Yeah,
Like you wouldn't get the 1, 2, 3, 4, right? And then you would just save that and move on, start at 4.
yeah.
Arithmetic subarrays, how do I make so many subarrays? How many numbers of subarrays?
For there to be a great solution to something, we need to have one single subproblem left over.
Yeah, and this one does not really have a subproblem issue.
So if we do something like ignore the last element of the array and try to come up with how many subsequences are there in this array, do we know for sure? If we go back to the scheduling problem, we could select something for sure, and the subproblem was an optimal component of the solution. If we get rid of the last number here and say, given this, can we extend the solution to this to incorporate this last element? With dynamic programming, we can.
With greedy algorithms.
With a greedy solution, not necessarily. There are components of this problem that involve the sequence 2, 3, 4 and the sequence 1, 2, 3, 4. That means that we have to consider many things down here. It won't necessarily all expand.
Definitely gonna need to work right. At least I see it though. How many people?
So what are people thinking for a dynamic programming solution?
Every time you apply array that's good.
Yeah. Yeah. My solution to this is I'm going to parse this array. I'm going to put a sliding window of 3 over it. I'm going to try to identify all arithmetic sequences of length 3. That's going to be O of n. As I put a sliding window here, a sliding window here. And then I'm going to go back to each one of them and I'm going to attempt to extend it in both directions. Can I extend this sequence on the left or on the right? If I can, actually I don't even need to consider left. That already would have been caught in a prior iteration extending that to the right. So you only need to take each sliding window of 3 and attempt to extend that out to the right. Do we extend and get something of length 4? Do we extend and get something of length 5? And that's kind of an iterative solution that should work.
Oh, then, I'm. Not like it would be safe completely, and then we went back to see if you had.
Yeah, the absolute worst case, if the entire array is an arithmetic sequence, is that would be quadratic. But the average case would be linear because we don't, that's only going to be the case if there's a large contiguous subsection of this array that is the arithmetic sequence.
How that's.
Yeah, it is kind of a, it almost is a kind of greedy solution in that every sequence that is longer than 3 will contain a 3 in it. So dynamic programming would say, we're going to look at the entire array and break it down into components. We're going to say, let's start with just one of length 3. Based on that, we're going to now expand. When we add a 4th character, the subproblems here are the subsequence here and the subsequence here. And we add another character and so there are going to be overlapping subproblems when we do that. So we just have to make sure that we store the overlapping subproblems and solve them. Look them up rather than solve them again.
Yeah. Suppose.
Kind of break this down into an array that is smaller, an array that is smaller, an array that is smaller, and start to do that. The absolute brute force way is to pass a sliding window of size 3, and then a sliding window of size 4, and then a sliding window of size 5, and a sliding window of size 6. Checking every element is going to be a sequence, but we can avoid a bunch of repeated work there by recognizing that every one of these is going to be an extension of sequence of size.
So that would look like a for loop that's like for the whole thing. For loop on the inside, that's like thing based.
Yeah, only if we have a sequence of size 3, then increment and find. I think that, to me, is what I would implement. That is worst case quadratic, but there are worst case a quadratic number of outputs here. As this scales, what is the largest size output? If nums were size 10, what is the largest value output could be? How could we solve that? Close. How many windows of size 3 are there in an array of size 10?
Let's see, how many windows?
Yeah.
So if there are 10 elements, well, normally you have 3 separate ones you get. 3 divided
We would have
3 by 3 is 9.
1 to 3, 2 to 4,
Yeah,
all the way down to 8 to 10. So the number that is on the left here is 8, which is n minus 2. How many sliding windows are there of size 4? This looks like a familiar sequence.
it does.
So this would give us n minus 2 times n minus 1 over 2, which is, again, quadratic. So that's how I get the quadratic number worst case.
Okay.
It shows up so many times. It's everywhere in this view.
Math checks out on the school.
Questions on this example? And I guess I should clarify as you think of those questions that if I throw something like this on an exam, I anticipate breaking everything down and looking for significant amounts of partial credit, because I'm not going to expect that you have an absolute perfect answer for every one of these subproblems. I'll be looking at the work that you do. What is your thought process? How are you solving this problem? How good are your solutions? Can you think about a problem in terms of dynamic programming and break it down into something that makes sense? Even if you're wrong about parts of a solution or whether a greedy solution exists or not, I mean, looking at your thought process, how did you think of the problem? So these are certainly not all or nothing kinds of questions. Right, you ready for another? Should these be answered as a logical explanation of our breakdown? Probably yes. You can, I'm not going to expect that you throw a bunch of math on an exam page, given that we don't really think about this mathematically. It's not our first. That's not how we think first. So yeah, you should be, if a question like this shows up on an exam, I would recommend that people think through each of these steps and throw down your thoughts on the page. This is what I'm thinking. This is how I would plan to do this. And even if it's not perfect, then I can look at your thought process and give you some credit for that. And then, yeah, dump every thought onto the paper in order to get as much partial credit as possible. Kind of. If you say things that are wrong or are bad assumptions to make, then you will find yourself losing points for your thought process. So throw things down on the page that make sense, that they'll just try to make things up in order to try to get partial credit. But yeah, if everything that you have, every thought that is productive or works toward a solution, then I would throw that on the page.
Bring extra sheets of paper.
Slate your work.
I prefer even more thoughts.
Oh,
Very
yeah,
long
I'll try to
explanation.
leave you plenty of space on the exam for that. But yeah, if you want to bring some extra paper, that's fine. I'll do this blank. All right, here is, we can at least start thinking about example 3. This one's a little bit smaller. We have an integer array again. Adjacent integers perform float division. So if we pass in an array of 2, 3, 4, it's evaluated as 2 divided by 3 divided by 4. However, we have the ability to add parentheses at any position to change the priority of the operations. We want to add parentheses such that the value of the expression after the evaluation is maximized. We want to return the expression that maximizes the value of this rather than evaluating in string form. So example 1 says we're past 1,110 and 2. And the best way to maximize the division of this, since there's going to be 1,000 divided by 100 divided by 10 divided by 2, where do we place the parentheses so that we maximize the value of the expression? And the correct solution is that we put parentheses around the last 3 numbers. 1,000 divided by 100 divided by 10 is 10, divided by 2 is 5, 1,000 divided by 5 is 200. That's going to be the largest possible value. And no matter where else we threw the parentheses, we get something that is less than 200.
If there's a pattern, I'm supposed to see.
We have a few minutes to go. If you have any questions on the study guide, feel free to raise your hand and ask them as well.
So by what time will these questions be on Canvas?
I have a meeting right after class, so I'm gonna need about the first 30 minutes of my office hours for that meeting. Depending on how busy office hours after that, I can either get these posted during that period. But worst case, they should be up after my second class, a little after 1. So I'm gonna say if they're not up by 2, send me.
And what about the lecture video?
I will also look over lecture videos and get those up to date today as well.
Would we have to account for values and that would flip?
Yeah. So there's nothing that says, according to these, that actually it does. So the constraints that are down here says the length is between 1 and 10. And each value of nums is between 2 and 1,000. So we actually do not need to account for negative numbers in this. But if we did, that would change things a bit. That would make things a lot more interesting.
The programming figure right now?
Yeah.
I feel like once you figure out what size numbers you want in the parentheses, you can do that type of thing.
We are actually out of time.
You gotta be kidding me.
So as I mentioned, I need about the first 30 minutes of my office hours for a meeting. And after that, I can handle anything that comes up. My anticipation for tomorrow, since we didn't get through everything, we'll review tomorrow as well. Please come prepared with questions on the study guide. I'll be asking that for tomorrow. And I can address any of those questions.
Maybe that will get today, just like one of them.
There's one more after this, I'd like to go over this and have that problem as well, but if there's anything else on the study guide that you'd like me to prepare in advance for tomorrow, send me an email and I can get additional practice problems up.
Alright. How do you guys think we need to do it?